The second half of Chapter 2 has us working with transformations, composite functions, and inverse functions. In 2.4, we're going to start by learning about certain types of parent functions. A parent function is just kind of the most basic form of a unique type of function. We've got 8 that we typically work with. A constant function would be when you just have an output value that doesn't change from your input. So a constant function is like y equals, that should be equals. In this case, it looks like about 1.25. This would be the example up above. So there's no x value that changes the slope of the line. An identity function is more commonly known as a linear function. And in this case, we have y equals 1x. So notice the slope is 1 and the y-intercept is 0. Nothing else is changed for that line. Absolute value is really easy to work with. No matter what your x value is, notice your absolute value is positive. So all the outputs are above the x-axis. And the last one over on the right, square root function. You take your x value and find the square root of it. Again, notice that all of our x values and all of our y values are positive here. Looking at the bottom 4, a squaring function is also known as a quadratic. Similar to absolute value, no matter what your x value is, your output is positive for the parent function. Now, a cubic function is going to be new for several of us. A cubic function, x can be positive and negative, and so can y. Notice it's not linear. It has kind of that curve in the middle. So this is going to be, I keep getting goofy things with my equal sign. There we go. X to the third power. So we'll have to be careful when we cube positive numbers and negative numbers. A reciprocal function is also known as an inverse function. And you'll notice a reciprocal function is unique because it has x in the denominator. So we're going to have to make sure we identify the values that x can't equal. And that has a name for the graph. The function that we're actually going to spend the least amount of time on, but it looks kind of the coolest, is called the greatest integer function. And what that means, it has kind of a double bracket on the inside with x. Like so. That's really weird looking. You can kind of see it right there. That looks better. A greatest integer function means no matter what your input value for x, your output value is the greatest integer part of that number. So if x is a fraction or a decimal, the output value is the integer that's in front of that decimal or the whole number for that fraction. We won't spend a lot of time on this one, but we will do a lot of work with transforming the other ones. To get a better idea of what the graphs will look like, we're going to draw some detailed versions of each type of parent function up above. Now this first one, I'm not sure where the little top part is coming from on here, like these parts right there. This is supposed to be absolute value, so I must have picked the wrong form for the boundary on each side. So I make sure those are just straight up and down bars. There shouldn't be any little part on the top of that. So this is absolute value. Anytime you have the bars on each side, this will be the parent function that we work with. Our domain represents all possible input values. And the values go from left to right forever and ever, so we would say x will equal all real numbers. We can plug in anything we want for x. Our range, or our output values, since absolute value always represents positive outputs only, the distance away from 0 on a number line, we're going to say f of x for our output has to be greater than or equal to 0 for the parent function. Now the absolute value has a turning point like a quadratic function does, and that is the vertex. And the vertex will be at 0, 0. As we make our table and pick points to plug in for x, we're going to always start with this vertex. So let's put a dot right away at 0, 0. All right, so to get an idea of where this graph comes from, we're going to plug in values for x to this equation. We already know 0, 0 exists. If we go 1 to the right, the absolute value of 1 is itself. But check this out. If we go 1 to the left, so over to -1, and we plug it in for x, the absolute value is also 1. Let's plot those 2 points. We've got 1 on each side, so it reflects over that y-axis. Now if we plug in 2 and -2, the same thing will happen. Absolute value is the same for both of them. So I'm going to go again, 1 to the right and up 1, 1 to the left and up 1. If I pick 3 and -3, and we plug in absolute value for both of them, our output, once again, is positive. So I'm going to go up 1 over 1 to the right, up 1 over 1 to the left. Notice each time, since there's no number in front of x, the number in front technically would be 1. So I'm going to write a equals 1, since this is the parent function. And what that means for absolute value is we're going to go up 1 over 1 in both directions. If you recognize that's the rule for absolute value, we can continue that pattern and then connect our dots all the way to the edge. So I went up 1 over 1 to the right and up 1 over 1 over here to the left. We'll connect those over here like so and do the same thing over here. So there's kind of the detailed form for the graph of the absolute value function. On the right, we have f of x equals x squared, and this is our quadratic function. We worked a lot with quadratics, but we didn't actually start with the parent function. Similar to absolute value, for quadratics, your domain is going to be anything you want for x. We talked about that back in chapter 2a. We can square any number we want. But for the parent function, our range will always have positive outputs. If you square a negative or positive number, your answer is always positive. All right, so we are going to start with, what did I say before? Hang on. Oh yeah, we're going to start with the vertex, sorry. Similar to absolute value, the turning point of a parent function is going to be right at the middle, at 0, 0. And if our a value is 1 here, since it's being squared and not absolute value, we don't have the same pattern to connect our dots. So we are going to have to make a table. And we'll plug in, we'll start with 0, 0. Now the first number doesn't really hold true with what I just said. If we plug in positive 1 and we square it, we get an output of 1. 1 squared equals itself. And if we plug in -1 and square it, we also get positive 1. So far, it looks just like our absolute value function. But watch what happens when we plug in 2 and -2. If you square 2, you actually get 4. And if you square -2, you also get 4. So if we go over 2 units, we have to go all the way up 4. Here's where that graph starts to kind of curve a little bit and become nonlinear, unlike that absolute value graph. And if we plug in 3 and -3, it goes all the way up to 9, and that's going to actually put us slightly off our graph. If I go 3 to the right and up 9, puts us slightly off, -3, up 9. So you can see those dots are not linear. If we connect them from left to right, we go down and then right back up. There we go. And there are the graphs of the first 2 of our parent functions. Our next graph is our cubic function. Like absolute value and quadratics, our domain is going to be all real numbers. Our range, unlike absolute value and quadratics, is also going to be all real numbers. If you cube a positive number, you get a positive answer. If you cube a negative number, you get a negative answer. Now this one doesn't have a vertex, but we are going to start right at 0, 0. We'll start right at the center. And if you cube 0, you get an output of 0. If we plug in 1, 1 cubed is also 1. So it starts off very much like the other 2. But if we plug in -1 and cube it, we don't get positive 1. So here's the change. -1 cubed actually goes right back to -1. So it almost looks like it's going to be a linear function from left to right. But watch what happens if we plug in 2. if you cube 2, 2 times 2 is 4, times another 2 goes all the way up to 8. So at 2, we go all the way up to the top of our graph. How's that for not linear? And if we plug in negative 2 and cube that, negative 2 times negative 2 is positive 4. But if you multiply that by negative 2, you get negative 8. And that's all the way at the bottom of the graph. We're supposed to try to connect these, so it's going to go up through that bottom point, make its way through those points in the middle, and then go straight up all the way up to the top. And that is the parent function for x to the third, or a cubic value. Our next graph is going to have a restriction in the domain. Notice for this function, x is in the denominator. We know that all fractions are possible except for one key fraction, when x is 0 in the denominator. For our domain in this function, x can't equal 0. Here's the unique thing for our range. If x can't equal 0, we still have 1 in the denominator divided by something. That means our output can't equal 0 either. So we're going to get something unique on the graph that we haven't talked about yet this year, but hopefully this sounds familiar. We're going to have boundary lines called asymptotes. And it's a really weird word to spell, but what it means is it's kind of like a boundary line that we don't cross over. So unlike our axis of symmetry with quadratics where we flipped it over the symmetry line, this is kind of like a boundary line. So our boundary line is going to be x equals 0 and y equals 0. It really just cuts our graph into different quadrants. And I did them in reverse order, sorry. That's the y equals 0. And up top, from top to bottom, whoops, that's our x equals 0. So what that tells us for this graph is we're not going to cross over either of those lines. As we make our table, notice we can't plug in 0, 0. 0, 0 is not possible. So I'm going to start with positive values only for x. I'm going to kind of divvy up my table a little bit. I'm going to pick values for x that are greater than 0, like 1. If I do 1 divided by 1, that's easy enough. But if I plug in 2, 1 divided by 2 is 1/2. If I plug in 3, it gets even smaller to 1/3. Watch what happens if I plug in 1/2. If we have 1 divided by 1/2, that would equal 2. It's just a reciprocal. And if we have 1/3, even smaller on the x value, that would go up to 3. If we plot these points, 1, 1, 2, 1/2, you see that it starts to get really close. That point is really not very good there. This gets really close to that bottom value, that boundary line y equals 0. And if I go to 1/2, I'm going to go up to 2, and then 1/3 up to 3. So you can see the curve for this shape of the reciprocal function. It goes edge to edge, and I should have probably picked a different color for that, sorry. It'll go edge to edge, getting infinitely close to those asymptote boundary lines, but not crossing over. And if I pick values for x in a new table that are less than 0, so this is very reminiscent of a piecewise function from our last chapter. If I pick the same x values but make them negative, -1, -2, -3, -1/2, and -1/3, the unique thing about this graph is my output values will be the same but negative as well. I'll have -1, -1/2, -1/3, -2, and -3, all from plugging it in for x in that reciprocal function up above. Plot those 5 points and sketch the curve down in the opposite quadrant. So as you can see, this graph is very unique looking and it doesn't cross over those boundary lines. Our last graph is going to be our square root function. We said for the domain, as long as x is greater than or equal to 0, back in chapter 1 or 2a, that this would be a function that exists. So as long as x is positive, remember our outputs were also positive. And if we have a domain restriction greater than or equal to 0, that's where we're going to start on our graph. So x equals 0 would be a square root of 0. We'll plot that right here. If I plug in positive 1, the square root of 1 is 1. So we get some consistencies with our prior graphs. But if we plug in 2, the square root of 2 isn't a perfect square. It's approximately 1.4. So if I go over 2, I'm just going to go up a little bit more. Another number that would be great to plug in would be 4. The square root of 4 is 2. And that's a consistent point to graph. The next perfect square would go all the way out to 9, and that will put us off of our graph on the x-axis, and the square root will be 3. So if we go out just a little bit and up, you'll notice our starting point right here is a closed dot, and we're going to connect through those points over here on the right. So it's kind of a curve, although my graph isn't showing up super well, that goes over infinitely to the right on the x-axis. As we look at performing transformations in upcoming lessons, you may have a number that's out in front of x, you may have something being added or subtracted to x, or you may have something that's being added or subtracted after. So each of these parts in a function or in an equation will be some sort of transformation. The a value is always going to be multiplied, so maybe you'll have a times x squared, or you'll have a times the square root of x, something like that. If the absolute value of a is greater than 1, we would say that this graph will stretch compared to the parent function. If the absolute value of a is between 0 and 1, so if it's a fraction out in front, we would say the graph compresses, and it'll look different from the parent function. If a is negative, the graph will reflect over the x-axis. So these will be words that we use to describe types of transformations. If we have an x minus h, like x minus h squared, or 1 over x minus h, the h value will either move it to the right or to the left. So if it's x minus h, the graph will move to the right h units, because it always goes in the opposite direction, if you remember from vertex form in a quadratic. If it's x plus h in the formula, it'll move left. That same amount. The k value is anything that's being added or subtracted after the x value or the x variable, and it isn't in parentheses with x. So maybe you have something like, I don't know, x squared plus k, where k is kind of separate from the quadratic term. Or you have absolute value of x plus k. So k is going to move up or down the same amount. So if it's plus k, you'll move up k units on the graph. If it's minus k, well then you'll just move down k units on the graph. Having this kind of detail will help us in our next lesson 2.5. And that'll be it for our notes today.